So the next speaker is Jwala. So Jwala is a PhD student at Nanyang Technological University at Singapore, and her research interests are in discourse-level machine translation with a focus on evaluating systems, particularly for discourse phenomena. She has published a list of papers on this topic. And today she will give us a talk benchmarking context-aware MT systems, test sets, and the evaluation measure for pronominal anaphora. So now the floor is yours.
Oh, thank you. Just give me a second to share my screen. Is it was? Are you able to see my screen?
Not yet.
Sorry, please give me a second. Oh, I'm not sure what's wrong. Oh, is it okay if I restart Zoom? I'm so sorry. I think there's some issue with the...
Yeah, of course. Yeah.
I'm sorry. Let me just restart it. Okay, is it working now?
Yeah, now it works.
All right, I'm so sorry. Thank you so much for your patience. All right, so hello everyone, I'm Jwala. And I'll be presenting my PhD work on benchmarking context-aware empty systems, where I'll talk about the test sets and evaluation measure for pronominal anaphora. So I'll start off briefly by talking about the motivation, and then I'll talk mainly about how we created diagnostic test sets and an evaluation model. Then we'll use these diagnostic test sets and evaluation model to benchmark some context-aware systems and look at the error analysis. And finally, I'll end with some discussion on the limitations of our approach. So I think this is probably something that everyone is familiar with at this point. So there've been fair amounts of claims of human parity and so on across different languages. And I think everyone here would probably agree that it was probably built too fast. So there have been several studies which have shown that this is not true. And mostly the problem has been that the evaluation is not really robust. So one of the main things that empty systems are still poor in translating are discourse phenomena. like pronouns, connectives, coherence, and so on. So today I'll mostly be concentrating on pronouns. So here's a very classic example of things of pronoun translations that empty systems still happen to get wrong. So we're translating from French to English, and we have an ambiguous pronoun in French, il, which should be translated to he, and empty systems most often tend to translate it to it. But here's a more, I think, interesting example. So here's a translation error from when we're translating from German to English. So in this case, the translation should originally be, I was shown this apartment in Earl's Court by Maria, and it had a red table. And the original German pronoun here is ambiguous, so the empty system produces a different translation. It says, I was shown this apartment in Earl's Court by Maria, and she had a red table. So the only difference between these two translations is the pronoun, which the empty system produces she instead of it. But the interesting thing about this example is that it completely changes the meaning of what we derive from these translations. So in the first case, when it says it had a red table, we infer that it's the apartment that has the red table. But in the second case, we would assume that it is Maria that has the red table. So there is a significant difference in what we perceive from these two translations, despite the fact that it's just a one-word change. So as I'm sure everyone will agree, BLEU is inadequate because it's not sensitive to these small differences. And it's not just BLEU. I think examples of this sort, I think, make a case for why we might need fine-grained evaluation and specifically targeted evaluation, because any sort of overall metric is not going to be sensitive or going to be able to point out these kind of problems with the translations. So there are some existing targeted evaluation measures. There are reference-based metrics where you usually match lists of pronouns. And of course, there have also been contrastive test sets with contrastive pairs where you're given a context and two options, and your machine, you assume that the empty system correctly models context if it assigns a higher probability to the correct sentence given the context. Of course, the problem here is that you cannot actually guarantee that this is the translation that the empty system would produce if it were to translate the source. So let me now introduce the diagnostic test sets that we built. So what we wanted to do was ensure that these diagnostic test sets were not synthetic. So we decided to base this challenge on real empty errors. So what we decided to do was to look at errors in WMT submissions. Since they release all of the system submissions that they get, all of the outputs, they release them every year. So what we did was we aligned these empty outputs from the WMT submissions with the references and found the cases where there was a mismatch in the pronoun translation. The idea here was that since every year these empty systems are usually one of the best systems that you have for empty, any errors they're making would signal particularly hard context for translation. So if there is an empty system making an error or several empty systems making an error for a certain case, we know that you can take the corresponding source and reference to sort of form a challenging sample. So here's an example of how that would work. So let's say we have some source and the reference says, I will miss him dearly, and the empty system translates that to we will greatly miss, and there are some other errors as well. So you align these two and find that I and V don't match. And so we think, okay, this must be a hard example for the empty system to translate. So the source and reference would be added to our challenge test set. We also generate something called a noisy reference, where we replace the correct pronoun in the reference with the incorrect pronoun that the empty system has produced. So basically, your noisy reference, the only error in the noisy reference will be the pronoun translation. I'll talk a little bit more about why we do this, but mainly we use this for evaluation and to conduct a user study. So as I mentioned, we conduct a user study to confirm if these translations are in fact non-equivalent, because just because they don't match doesn't mean that they're wrong. So I'll describe the user study in the next slide. But one of the advantages of using WMT is that I think from 2011 and so on, they've actually started including document boundaries. So we have that information, even if the empty systems don't necessarily use it. But also more importantly, they have several source languages, although we in this case, we only concentrate on target English, we are able to build test sets for several different source languages because they have campaigns for lots of different languages. So it's very easy to generate test sets for different languages. And because we're doing this automatically, it's also quite easy to update these test sets as models improve. So every year models get better, the challenges can get harder. So whatever is easier, we can stop including it in the challenge test set and then make this harder and harder as the models improve as well. So this is what our user study looked like. And what we did was we actually conducted this across different languages for German, Chinese, French, and Russian. We gave them a one sentence context, the source, and then we showed them the reference and the noisy reference to make sure that there's no other errors that they can be influenced by. The users didn't know which one is the reference or which one is the noisy reference, and they're just asked to pick if the translations are correct or if they're tied and so on. So the idea here is that this way we find pairs of pronouns which with very high agreement would never be equivalent translations given any context. So that way we can automatically then assume that any machine translation error which is one of these pronoun pairs given a reference translation is definitely a wrong translation. Therefore, we can include it in our challenge test set. And whatever we have low agreements for, we know that they're likely to be equivalent. There are some contexts where they're interchangeable, so we don't consider them to be wrong. We also did this study without the source monolingually, just to sort of check if it would hold in that case as well. And we found good agreements across the board. Let me now talk about the evaluation model. So given that we now have a test set, how can we build some model-based evaluation to do like a little more nuanced evaluation of the pronoun translations? So the idea was that we would train a model to distinguish good and bad pronouns in context. So we want to look at the previous sentences while we do this evaluation. So here's an example of some translations from the reference and the system. So we have the previous sentence context and the current sentence. So if we look at the reference, there's a nice co-reference chain that all agrees with each other. So he laughs and recalls how his father and so on, and 7 years later, he was back. So there is a co-reference chain here from the previous sentence to the current one. If we look at the system translation, there is also a co-reference chain there, although it's completely wrong. So the translation is poor, but the system consistently translates it incorrectly and translates it as it's and it instead of he. But if we were to look at the reference and then compare the current reference translation versus the current system translation, then it becomes a little bit more obvious that the system translation is wrong. So looking at the reference context as sort of the common context, then it becomes easier for the model to learn to look at errors. The idea is that we'll use pairwise ranking to score the reference pronouns higher than erroneous empty system generated pronoun translations. So here's what the full model looks like. I'll break this down, but the main idea here is that both the reference and the system translation go through the same model, that the parameters are all shared. And finally, there'll be a pairwise ranking loss at the end. So I'll start from the bottom up, and as an example, let's look at the system translation. So the first thing we do is to get representation. So this is a slightly older model, so it uses Elmo. We did also try this with BERT, and there wasn't a significant improvement in results. The limitations of this model are not really because of the representation, so I think we can probably set that aside for now. So once we get representations of the current sentence, we have this attend over the context. So this is usually the previous sentence. If context is not available, then it's essentially self-attention. Then we extract the pronoun representations from this sentence, and the idea is that we will only score the pronoun representations. So in the next step, we have these pronoun representations attend over the representations we got previously. So at this stage, we should essentially have pronoun representations which have looked at its own context from the same sentence and also the previous sentence context. And once we have that representation, we then just have a linear layer that reduces this to a score. And then these scores will then be fed into a pairwise ranking loss, where then the idea is to train it to assign a higher score to the reference pronouns and a lower score to the system translation. So what we do is, as I described the way we filter the challenge test set, we actually just use some of the older data from WMT to train this model and the newer data to test it. And we found that in general, without context as well, the model is reaching about 89% accuracy. But then if you include a common reference context, the accuracy improves significantly. And the model is good at distinguishing both the noisy reference, the R prime here is the noisy reference, where there's no other error except pronouns. And so the model has fairly good accuracies. But more importantly, we compared the agreements with the human judgments on the user study, and we found that this model has a fairly high agreements with human judgments across the different languages. So we then looked at the attention maps to see where likely the model was looking at when it was producing the score. So here's an example. So we have a clear case of an error here where you have it claims the money was going towards a headstone for her son who died. So it should have been she claims. And we see that the model does seem to be looking primarily at it. So the point here is that the model actually doesn't receive any signal about which particular pronoun is wrong. So we actually just give it a reference translation and a system translation and just say score the reference one higher. So it doesn't know which particular pronoun is wrong, but it looks like it's looking in the right place. So it's learned to do that after looking at lots of different examples of errors. Here's, I think, a more interesting example. So we have a reference where we're talking about Biles, who became the 4th consecutive American woman, consolidating her reputation as the best of her generation. So this is the reference translation. And if we look at system 1, it's produced consolidating its reputation and the best of his generation. So the model gives it a lower score compared to system 2, which produces his reputation and his generation. So the model gives this a slightly higher score than system 1. So this is mostly because there's consistency in system 2. So the way the model has been trained is that it sort of looked at these score reference chains through the reference context and the current sentence and so on. So the model does tend to give a slightly higher score if you're more consistent, as opposed to simply marking it all wrong. So compared to, let's say, metrics that would just do comparison with the reference, there is a sort of nuance in terms of evaluation that happens here, where if you are consistent in your translation, you tend to score slightly higher than an inconsistent translation, even if it's wrong completely. So there are some cases where the model does get it wrong. So in some cases, like where we have ambiguity and where the agreement in the user study also tends to be low. For example, we always tell victims not to pay up. That simply exacerbates the problem versus it simply exacerbates the problem. So these are some cases where there's ambiguity, where it doesn't matter if you replace these pronouns. But I think more importantly, where the model gets it right is when he is replaced with it. So this is actually, turns out that this performance actually just follows the distribution of the training data, because a vast majority of errors that empty systems were making was in this particular case, where they would produce it instead of he in a lot of the time. So in that sense, the model performance is strongest where empty systems are most strong, because that's where a lot of the training data comes from. So now that we have test sets, and now we also have an evaluation model, we now move on to benchmarking. So we benchmarked about 7 different context-aware models. Actually, 4 of them are context-aware, while 2 others are sort of use a previous sentence context, which is concatenated. So the first one is just a sentence-level model. The next one that we're calling concat just concatenates the previous sentence for context. We also trained MBART in that same setup, and then 4 other context-aware models from different sources. I won't go into the details of the architecture, but in general, they all have a separate encoder for source context and fuse them through gates, and some of them they have hierarchical attention fusing target context and so on. So I would refer you to the original papers for the full architecture, but I'll move on. So yeah, we trained all of these models across 3 different language pairs. So with German, Russian, and Chinese to English translation. Unsurprisingly, MBART has the highest BLEU scores. But in general, I think if you look at German to English, for example, most of the context-aware models have very similar BLEU scores. I think there's slightly more variation in Russian and Chinese. Okay, so when we then we ran all of these models on all of our test sets for these different language pairs, and then we used our model to rank them. And these are the overall rankings that we got across the different language pairs. So we see that MBART is on top for German and Russian, and it's also sort of in the top half for Chinese. But if we look at some of the other context-aware models, we see that they're far less consistent. So Anaphora is kind of doing poorly for German, while it's doing somewhat okay for Russian and quite well for Chinese. So overall, we see that the context-aware models are sort of more inconsistent. They tend to do poorly, or they do well in one particular language pair and poorly in another one. So MBART turns out is far more reliable in that sense and generalizes better. So it's good in 2 and in the top half in Chinese. And even Concat, for that matter, it does not do that poorly. It's in the top half for most of the language pairs. So it seems they're far more consistent compared to context-aware models. So let's look at some of the examples that of the errors that the context-aware models tend to make. So here's a reference where we have the players will see this course at its finest. It is in fabulous condition. And the Anaphora model translates this as we'll see this course from his best side. He's in a great state, so it's producing he instead of it. And Concat is producing this correctly, so the model gives this a higher score. So here's, I think, a more interesting example. So we have the reference which says Alois didn't know how to help Auguste, but he watched over her until sadly she passed away. And Anaphora is producing Alois did not know how Auguste should be treated, but she was concerned about her condition. So there's an error here. It's producing she instead of he. But if we look at the output produced by the source attention network, it actually skips the pronoun. So it says Alois doesn't know how to treat Auguste, but has always paid attention to her condition until her death. So what happens here is that it doesn't produce a pronoun, but that means that it isn't producing an incorrect pronoun. So the model gives this a slightly higher score than it gives the previous translation. So, and in some sense, this is a better translation because it skips that pronoun. It does actually make a little bit more sense than Anaphora. So the model does give this a slightly higher score than the translation that Anaphora has produced. So doing some more analysis of the kind of errors that these models were producing, most common error was that they would copy grammatical gender from the languages that they were translating from. But I guess the harder task would be where they were trying to infer gender from named entities, which they inferred incorrectly. And of course, more commonly, we'd have ambiguity. And in case of Chinese, you'd have pro-drop, where the model struggled as well. Interestingly, we saw that there was a greater diversity in the pronouns that were produced by the contextual models. So what would happen is the sentence-to-sentence model, for example, almost always produces it in a lot of these cases. But even though they do, the context-aware models had more incidences where they produced he or she, they were usually producing them at the wrong time. So like the previous example we saw, the sentence-to-sentence model might produce it in that scenario, but then Anaphora would produce she, but they would both be wrong. Okay, so let me now talk about some limitations of our work. So the first thing is that although our effort was to try and make sure that it was generalizable, we could produce the test sets and build the models across different languages, we did make that assumption that pronouns would be separate morphemes, which is quite easy in English. It's easy, it's a closed set, you can match and filter things quite easily. But if you have languages where they're not separate morphemes, it becomes a little bit more complex. But I think a more, critical sort of limitation is that we are not really training the model to detect equivalent translation. So it's explicitly being trained on more serious errors, and we sort of discarded most of the equivalent translations during the user study because they're a little bit more complex. So that is a limitation of the model, in that if there are two equivalent translations, we won't really know about it. And another limitation is that when we did the filtering for the data set, we did not actually impose a constraint to require context for translation. So we were looking at errors, and we know for a fact that these are hard cases for empty systems to translate, but there isn't a constraint as such which says that you need context to translate these cases. So it's possible that it's not really necessary. we did see some results where including context improved the evaluation, but it was not a very significant improvement. So there are some cases which need context, but maybe a lot of them don't. But one thing to note is that that doesn't excuse the context-aware models from failing on sentence-level cases. So there's no point in improving context-level pronoun translations if you're going to do poorly on the sentence-level cases. So I think their poor performance is still to be held accountable, even given that this is a limitation. Okay, so that's it for my presentation. Thank you very much.
Thanks. So we still have some time for questions. Any questions from the audience?
I have one question. So if I understood you correctly, your approach relies at least partly on word alignment for those phenomena. And one thing that I have observed in trying to align pronouns and stuff is that you just never really know what the statistical word alignment does, and you don't even really know what it's supposed to do. So I wonder if you could comment on that and how that has, what effect that has had on your work, if any.
Right. I mean, that is true. So there was, I think, a fair amount of work to be done in the beginning to make sure that the alignment was making sense and so on, especially when there are multiple pronouns. When there is a single one, it makes, I think, which is in a majority of cases, it's much easier. But when you have multiple pronouns, it's a little bit harder. I think what we did was, because we stuck to English, it sort of made a lot of our work easier, because it is a very close set. There's a very short list of pronouns. I mean, even if you look at all of we included everything like who, where, what, and so on as well. But even then, it's a relatively short list. So it did simplify a lot of our task because of that. I think if you switch to a different language, I think it would definitely be much harder, which is why I pointed that out as one of the limitations, because it would definitely get far more complex if you were to move to a different language where things were not so easy.
Yeah. Have you ever developed any formal guidelines for like how for word alignment of pronouns, or did you just decide case by case whether things made sense?
Yeah, that's pretty much what I did. But I think that's a good idea.
Okay.
Actually, I should probably do that and sort of document everything and make a formal.
I mean, it's what most people do, but I mean, I have sometimes wondered if we really need it, if we wouldn't need actually some more like theoretically justified guidelines for that. So
yeah, I think
I would be very interested
sort of
in seeing any if you develop them.
Right. So I think here we sort of just depended on the numbers in many ways, because we had a big corpus and lots of different systems. So like across different years and different system translations for the same source and so on. So we sort of just depended on the numbers and then just went with the majority in the sense, and hoping that that would be reliable. So I think that's probably where the formality of it sort of got lost. So that's
that
a
makes
good
sense.
point. So.
Thank you.
Yeah, thank you.